Hello and welcome to lesson 5.2, instantaneous rates of change using the difference quotient. So yesterday we were introduced to the difference quotient. It is of the form f of x plus h minus f of x all over h, with h values being very close to 0. So this is a possible suggestion for the value of h. Now, you could change your variables, you can change your function, doesn't matter, it's usually of the same format, okay? So, using this, what we can do is we can calculate the instantaneous rate of change of a function at a specific point. So let's take a look at this function right here. So first notice that this function can be written as f of x is equal to the square root. I'm going to factor out a -3 here. Or it can also be written as -3 times x minus 3. As you might realize, this is a square root function. Has a x-intercept of x equal to 3. And has values that are less than or equal to 3. So you can only choose values less than or equal to 3 to work out the instantaneous rate of change. So using our difference quotient, we're going to calculate f at 0 plus 0.0001 minus f at 0 all over 0.001. Use your calculator and keep all the values accurately. Although you're keeping the values accurately, you're actually having these values rounded or approximated, so they're not exactly the right value that you see right there. There's more not actually showing. If you work this out properly, you should get a value of approximately -0.5. So there you see the instantaneous rate of change at the value of x equal to 0 has a slope of approximately -0.5. Most likely is -0.5. Okay, so what you could also do is you could simplify the difference quotient. You can simplify the difference quotient by either substituting the x value in right away, or you can substitute it later on. So let me show you how this would work instead. Okay, so this time we're substituting x plus h into the function. We're subtracting the function x squared from it. Sorry, f of x, my apologies, which is x squared plus 2x. This is going to go all over h. Don't forget the all over h part. Now, what you do is you expand and simplify, and then reduce as much as you can. So x plus h squared turns out to be x squared plus 2xh plus h squared. This becomes 2x plus 2h minus x squared minus 2x all over h. Again, you could have substituted the value of x equal to 3 in at any point in time, even at the beginning. You don't have to, but that's an option. And so if you do this properly, you'll notice that the x squareds cancel out. Same thing with the 2x's. So everything remaining should have an h in it. Now you can cancel out the h from the numerator and denominators, realizing h can't equal 0. Now, remember we are using a value very close to 0, but not exactly equal to 0. So now you can substitute those values in. We can work this out as 8.0001. Now, if we were able to put in 0 for h, you would notice that this is approximately the value of 8. So the only issue here is the actual value h being equal to 0. So you can choose values really close to 0. Doesn't have to be 0.0001. That's a suggestion, but it changes for each type of function. So let's see another instance of this. Here we're only asking for the instantaneous rate of change at x equal to 3, so I don't need to simplify the difference quotient. So I'm going to work out f at 3 at 0.0001 minus f at 3 all over 0.0001. Again, realize that this function x cannot equal 2. That's the only issue there. Okay, so again, use your calculator and be careful to keep all the values. If you don't keep all the values, your answer will be off. Very, very far off. And then you will lose marks for accuracy. And there you go. This is approximately -2. Okay, so we can use instantaneous rates of change to verify that we have a maximum or a minimum on a function. For a maximum, let me draw an example of a maximum. So here's our function, f of x. We have a maximum at this point. Well, you'll notice the slope at that spot is equal to 0. Slopes on the left side are positive values, so greater than 0. And slopes on the left are negative values. So what you can do is you can prove you have slopes to the left, that's positive, slopes at equal to 0, and slopes afterwards less than 0. Or what you could do is find slopes close to x equal a on left and right. Verify their signs and also verify that they're close to 0. So you can actually do this twice instead. And likewise, for a minimum function, so let me draw a function with a minimum. The only difference here is slope at the minimum is still 0, but on the left, the slope is negative, and on the right, the slope is positive. So again, you want to find slopes close to the maximum or minimum value at x equal a on the left or the right, and just verify that, verify their signs and verify that values are close to 0. Okay, so let's try this, and I'll show you how it works out with just 2 of them. So we're going to first look at left of x equal to -2. Okay. So if we're going to look on the left, that means instead of adding the value of h, we're going to subtract the value of h. So we're going to write f at -2 minus 0.0001 minus f at -2 all over -0.0001. Again, work out our values. So this works out to be 24.999999991 minus 25 all over -0.0001. This works out to be approximately 0.000900002. So here you can see on the left, it's a positive value. That's close to 0. So let's take a look at the right. So we're looking at f at -2, and this time we're adding 0.0001. Wow, interesting. This turns out to be 24.999999991 minus 25. Doesn't always work out that they're exactly the same numbers, but in this case it did turn out to be that way. Or at least it looks like they're the same numbers. When we actually work it out,
Good, how are you? Mike?
you'll notice it's a negative value, very close to 0. So therefore, we approved. We have a minimum. Oh, sorry, we have a maximum. And there we go.